we will start this lecture 15 with a thought process from Martin Luther King Jr. and which is quite true at this moment. Our scientific power has overturned our spiritual power. We have guided missiles and misguided men. So, it is very appropriate when we are discussing about propulsion, and which we will be discussing about missiles sometimes. Now, let us get into our usual things, and we will have to recall what we learnt in the last lecture. In the last lecture, I basically initiated discussion on the one dimensional flow with heat addition, and we have derived all the expression for the properties ratio across the heat addition zone, right. And then we looked at that those properties, for example, pressure ratio, temperature ratio, total pressure ratio, density ratio are function of gamma, m1 and m2. Later on, I also gave an what we call discuss about a relationship between the Mach number, inlet Mach number and outlet Mach number, and we found that it was quite difficult to handle. Then we devise a ways of referring to a sonic condition. For that, you need to express those expressions for the ratios, and so that you can solve very easily. And if you remember correctly, that we took an example where we use the reference conditions corresponding to sonic flow and then solve the problem. If you look at your notes, you will find that what we learned for the subsonic flow, that means that example was meant for subsonic flow, right. What do we see? That temperature at station 2, that means upstream of the heat, downstream of the heat addition will be greater than the upstream condition. But what happens to the pressure? Can you just look at your note? Pressure at the downstream condition of the heat will be decreasing, right. And what happens to the your density, and what happens to the total pressure and total temperature that we have seen. Now, we will try to look at what happens when the heat addition, right, instead of supersonic flow, and if it is subsonic. In other words, if the flow is subsonic, we have seen that something is happening, and if the flow is supersonic, what is happening? Will it really happen that just opposite that what is happening in the case of subsonic flow, that what we had discussed in the last lecture by considering an example, or something will happen different. So, let us look at basically the processes for both the sonic and supersonic flow is plotted in a Moeller chart, that is in the x what you call in the vertical axis, that is enthalpy, and in the horizontal that is entropy. We call it as a basically Moeller chart. If you can look at that, this is the curve which I have shown for both supersonic and subsonic, and if I consider a what you call a flow supersonic, right. If I add heat, what is happening? That means, if I consider this is the inlet condition, like this is corresponding to the station 1 inlet condition, where it is Mach number 1 is greater than 1, that means it is supersonic flow. For example, if it is 2 or 3 or something like that, right. Then if I add heat over here, then what happens at station 2? That will be dependent on the extent of heat being added. That means, it will be depending on the amount of heat which is being added to this incident. And we will see that, like if we go back to our expressions, that at the exit of this heat addition or the downstream of heat addition, there will be decrease in the Mach number. In the last example, when the flow is subsonic, what is happening when you add heat? Let us say flow is subsonic here, and when you are adding heat, then the Mach number at the downstream is increasing as compared to the inlet condition. But in this case, this is just opposite, that is Mach number at the downstream is less than the inlet Mach number, right. And as you goes on adding the heats, what will happen? If you look at the entropy also is increased, that means if entropy is here and then another place here, entropy is increasing, and it goes on increasing this Mach number in case of supersonic flow on heat addition till it attains the maximum entropy values, that is the sonic condition. What is the meaning of it? That means the flow is choked and it is thermally choked. That means you cannot really go on giving the heat further to change the flow properties at the downstream of the heat addition zone, right. And if you look at, suppose I want this flow as attain the sonic condition, right, and then I want to decrease the flow to subsonic condition, what I will have to do? I will have to cool it so that it will go in this direction and attain. And similarly, if I am at the subsonic flow conditions, right, and I am heating, so what is happening? That is Mach number goes on increasing, right. If you look at Mach number goes on increasing, and so also temperature is goes on increasing, but however till this point. After that, if you look at your enthalpy is goes on increasing till this point, after that it decreases, but however the Mach number goes on increasing till it attains the sonic condition, and also the flow is thermally choked. Beyond that, you cannot really add any further heat unless otherwise you change the inlet condition, right. And if you want to go beyond this, when you are coming from the subsonic, when you want to go beyond the sonic and to the what you call supersonic, then you will have to cool this so that you can reach the supersonic condition, right. So, just to recall that what we have learned, the Mach number increases in case of subsonic flow, that is M2 is greater than M1, and pressure decreases, P2 is less than P1, this is for the subsonic, and total pressure decreases, right, PT2 less than PT1, and temperature increases till M is less than equal to 1 over that, these values, right, this point, and then of course, after that further further addition of heat, it will be decreasing, right. That means, when M is greater than M gamma power to the minus 1 over 2, right. And total temperature of course, goes on increasing with the because heat being added. So, in case of supersonic flow, what will happen? Mach number actually decreases, that means M2 is less than M1, right, and pressure increases, P2 is greater than P1, and temperature increases, T2 is greater than T1, and total temperature of course increases all the time, and total pressure decreases, both the case if you look at whether it is a subsonic flow or the supersonic flow. Now, suppose you are having this what you call added, right, heat, and if you are in the choked condition, that means you are in the supersonic flow, right, if it is you are in the choked condition, thermally choked, and if you go on adding heat, what will happen? For example, you are at this point, what will happen? I am not changing the inlet conditions, but what will happen? Let us understand how we will get this supersonic flow, right. For example, if I take this a what to call a heating zone, and then I am this is a subsonic jet, what do you call, this is a CD nozzle, and then this is being added heat. So, if I am go on adding heat in this region, go on adding heat, so that this region, that is 2, it has reached as a what you call the sonic condition. If I go on adding further heat, if this goes on increasing, then beyond the choked condition, what will happen? It will happen that a shock, normal shock will be formed such that at the downstream this will be subsonic flow. Right, and then the condition has been changed. That means, you have gone to this region somewhere, and then you can have. But if it is other way around, the flow is subsonic and you are go on adding heat, right. At when it is choked condition, what will happen? At that point, it will be sending some pressure waves such that this condition, instead of at this point, it will to go over somewhere this point, such that the inlet condition will be changing, right. So, and now we will move into another topic, that is the constant area one dimensional flow with friction. Of course, whenever constant area is there, there will be one dimensional flow, right, and it will be a steady flow. And keep in mind that we have not considered the friction earlier, right, but now we will be considering friction, and there is no shock formations and others. So, let us look at a simple case of one dimensional flow, where the flow is taking place over here, right, and having certain properties of P 1, V 1, T 1, right. And if you take a small control volume, this is a small, although it looks to be big, but it is a small one having a dx, and it is having certain properties at the station 2, and you keep in mind that here we are considering there is a frictional effect on the wall, and this is your what you call on the wall, right. There is a frictional force here, stress, which is on the wall itself, right. And what we will do, we will try to analyze and see that what it is happening, particularly to the properties, right, at the station 2 whenever there is a friction. Keep in mind that these frictional forces will be dependent on what? It will be dependent on the properties of the wall, right. If it is a rough, if it is a smooth, and then it will depend on length of the tube what is being considered, right. So, let us make usual assumption, that is one dimensional steady flow, adiabatic flow, there is no really heat being added, no gravitational force, ideal gas we are considering with a constant thermodynamic properties. That means, it is a basically a calorifically perfect gas, and no work interaction across the system. That means, if I take this control volume, there is no work interaction. And what we will do, we will basically look at the continuity equation as we have seen, like this will be 0 because the flow is steady, and for this one dimensional flow, it is basically rho 1 V 1 is equal to rho 2 V 2, as A 1 is equal to the A 2 and A, that is a constant area duct. So, therefore, we will get this expression very easily. And momentum equation, if we look at, it is integral form is given, this is the unsteady form and the convective form, pressure, and this is the body force, and this is the wall shear stress kind of thing. Keep in mind that we are looking at in a very simplified way, and this body force is 0 and the steady is 0. So, what is remaining is your convective terms and this is your pressure of course, and if you will integrate it, the control volume will get rho 2 V 2 square A minus rho 1 V 1 square A and P 1 minus P 2, right, because although there is a negative sign it will become P 2 minus V 1, then it is being absorbed over here into area. And what is this F w? F w is equal to basically pi d by tau w dx, right, because like F w we have is nothing but your tau w, and keep in mind that this is the pi d is what? Pi d is basically area, this is the area, I mean what you call circumference, right, and then dx that we have put it. Now, if I will divide this expression by area over here, this will cancel it out, this is also is cancel it out, and this will be pi by 4 d square, right. If I do that, I will get an expression basically like the rho 2 V 2 square minus rho 1 V 1 square plus P 2 minus P 1. I have taken to the left hand side to the right hand side, I have taken this portion to that side, and then is equal to minus 4 by d, right, d cancel it out and pi is cancel it out, 4 by d tau w dx. So, if you look at this is the extra term which is coming, so far momentum equation is concerned as compared to the flow one dimensional flow with heat addition, right. So, we will be looking at this term, and let us now invoke the energy equations as having a unsteady terms and then convection terms and then heat interactions, shaft work and the body force. So, this is 0, this is also 0, there is no heat transfer. So, this will be 0, and this is we are also coming because the same plane and is unsteady. So, this is 0. Then it will be coming to the what you call with a usual form, that is H 1 plus V 1 square divided by 2 is equal to S 2 plus V 2 square divided by 2. What it indicates that total enthalpy along the direction of the flow or between the station 1 and station 2 remains constant. So, for an ideal gas equation we will be using P is equal to rho R T, that is a usual expression we have used several times, and differential form of continuity equation we can look at it, that is rho 1 V 1 is equal to rho 2 V 2. If you look at differential form, what it would be? It will basically d rho by rho plus dV by V is equal to 0, right. This is the form which we will be getting, and similarly we can look at the momentum equation in the differential rho V dV plus dP is equal to half rho V square 4 F dx by d. But what is this F? F is a coefficient of friction tau w divided by half rho V square. This is the coefficient of friction what we have included in this expression. Instead of tau w, we are putting basically F and taking that into consideration. And energy equation 3 becomes like dH plus V dV is equal to 0. This we have seen earlier, you can see very easily from equation 3 that equation 7 we can get. Now, we need to look at these expressions and then see how we can So, equation 6 can be written in terms of Mach number like and using ideal gas law of equation 4. That means, if you look at I can have rho V dV plus dP is equal to half rho V square 4 F dx by d. What I will do? I will just divide this expression by rho V square and 2, and similarly, so that I will divide this by half rho V square and this will be cancel it out, and if I will simplify, I will get basically 2 V dV because this cancel it out and then V cancel it out dV and 2 dP by rho V square and 4x 4f dx divided by d, right. And what I will do, I want to this portion in each term put in terms of Mach number, right. So, if you invoke this Mach number definition, we know that V square is equal to m square a square, where a square is nothing but gamma p by rho. So, V square is basically m square gamma p by rho. And if you differentiate this thing V square, you will get 2 V dV and then all terms you will be getting on the right hand side. And if you club together in this expression and expand it, you will get a express this equation in terms of Mach number, which turns out to be 2 1 minus m square divided by gamma m square into 1 plus gamma minus 1 divided by 2 m square d m by m is equal to 4 f and d dx. I would urge you people to derive yourself, and if you find difficulties, let me know. So, then equation 8 can be integrated between the x is equal to x 1 and x is equal to x 2, because we have taken a dx, and between the Mach number m 1 and m 2, and we can express this as minus 1 over gamma m square minus gamma plus 1 divided by 2 gamma ln m square divided by 1 plus gamma plus 1 divided by 2 m square, and this is between m 1 and m 2, and of course, the right hand side is simply kept as it is, that is 4 f by d dx x 1 to x 2. And we will be looking at this expression very carefully and how to handle that, because unless we know this m 2, right, we will be knowing m 1, we may be knowing the friction factor, and we may be knowing the x 1 and x 2, we need to find out m 2, which is not that easy to get that. So, let us consider that as the flow is adiabatic, temperature is remaining constant during this frictional being considered, then we can have expression for temperature ratio. So, if you look at temperature ratio T 2 divided by T 1 is equal to T T divided by T 1 divided by T T divided by T 1 2. What I am saying? I am saying is basically T T 1 is equal to T T 2, because from the energy equation, right. So, therefore, this portion I can write down as 1 plus 1 gamma minus 1 divided by 2 m 1 square, and this portion is nothing but the denominator of the equation 10, right, which is a very familiar form of expression what we you are used to. So, similarly, what we will do now, we will be getting expression for various properties ratios. So, from the continuity equation, I can get rho 1 V 1 is equal to rho 2 V 2, as a square is equal to the gamma p by rho, that is from the definition of speed of sound, I can get that gamma p 1 V 1 divided by a 1 square. That means, what I am doing? I am basically looking at this is the rho 1. Similarly, this is my rho 2. So, I am just expressing, and what I will do? I will just put this in the expression of in Mach numbers kind of things, and if I look at this, I will get P 2 by P 1 is nothing but A 2 square V 1 divided by A 1 square V 2, and if you look at like V 1, right, if I look at V 1 by A 1 is nothing but m 1, right, I can get m 1, and similarly, I will get V 2 by A 2 m 2, and what is remaining here is root over A 2, I can get root over T 2 and divided by root over T 1. And then I can get this T 2 by T 1 and plug here from equation 10 in terms of Mach number. Thus, we will get a expression for pressure ratio in terms of m 1 and m 2, which is very straightforward, right. what I am doing basically I am putting this T2 by T1 in this portion, right, in terms of mass. So, using equation 10 and 11 we can derive an expression for density ratio, right. That means, I can say that rho 2 by rho 1 is equal to P 2 by P 1 into T 1 by T 2, and P 2 by P 1, if you look at this expression, I can put it here, and similarly T 1 by T 2 I can use from that, and then I will get an expression that is m 1 divided by m 2 into in the bracket 1 plus gamma minus 1 divided by 2 m 1 square divided by 1 plus gamma minus 1 divided by 2 m 2 square power to the of course minus half. If you look at it, will cancel it out some of the things, and then you will get this expression. So, by using this equation 10 and 11 we can derive an expression for total pressure ratio, that is P T 2 by P T 1 is can be expressed as P T 2 divided by P 2, P 2 by P 1 and P 1 by P T 1. If you look at, I can use for here isentropic relationship, right. I can use for isentropic relation P T 2 by P 1, which is nothing but 1 if I look at this 1 plus gamma minus 1 2 m 2 square gamma minus 1, right. I can use that for that, and similarly I can this is 2. So, similarly for this I can use, and from equation 10 this expression I can use over here. If I do that, I will be getting what? If you look at, I will be getting an expression like m 1 and m 2 will be coming like this, and then I will be getting 1 plus gamma minus 1 divided to m 2 square, and from there it will be coming over there 1 plus gamma minus 1 m 1 square power to the gamma minus 1. So, if you look at what I will be doing, gamma minus 1 plus half, right, which will be 2 gamma minus 1, right, 2 gamma plus gamma minus 1, I will be getting basically gamma plus okay. I think there will be minus over here. So, minus and then plus. So, I will get gamma plus 1 2 gamma minus 1. So, I will be getting these expressions. So, therefore, I will get gamma plus 1 into 2 gamma minus 1. So, if you look at all the expression, what we got is basically in terms of m 1 and m 2 and gamma. Now, to to find out basically these ratios, right, we need to know m 2, right. Of course, we will be knowing the m 1, and but to find out this m 2, which is quite difficult. For example, I know these values, but naturally we what we will do, this m 1 will be known to you, right, but m 2 is unknown and this is known, and it is very difficult to estimate what will be the m 2. So, for that we will be using the sonic flow as a reference conditions, and where properties can be denoted by P star T star, and so that we can use this for our calculation. Hence, we need to derive the properties ratios for the reference conditions from what we have already derived. So, if you look at T 2 by T 1 is the expression what we got, 2 plus gamma minus 1 m 1 square divided by 2 gamma minus 1 m 2 square. What we will be doing, we will seeing that this condition m 2 is basically 1, that means this became 1, and of course, m will be m square, and T 2 will be basically what, T star, and T 1 will be T, So, if you look at this, what I will be getting? I will be getting basically in this expression as gamma, because 2 gamma minus 1 becomes gamma plus 1, and this will be 2 gamma minus 1 m square. So, if I just invert that, T by T star will be gamma plus 1 divided by 2 gamma minus 1 m square, right. That means, whatever the we have derived earlier, we can get this expression with reference to the sonic condition, right. Similarly, for the pressure ratio, we can get P by P star 1 by m into in the bracket gamma plus 1 2 plus gamma minus 1 m square power to the half, and rho by rho star 1 over m. I mean, I can get the similar expression only with the pressure, only the sign is changing, that is minus, right. And total pressure, we can also get the expression for the with reference to the sonic condition, that is the P T star, and we can get from this equation 9, because as I told that this expression will be equal to 1, right, for the sonic condition. So, when it is 1, then you will get 4 f L star, because I am integrating for the certain length, that became L star divided by d is equal to 1 minus m square divided by gamma m square, and this expression is same rather with a positive sign, that is gamma plus 1 divided by 2 gamma ln in the bracket gamma plus 1 m square divided by 2 gamma minus 1 m square. And where f is basically the friction factor being integrated over the initial 0 to the L star length, right, because it is going to the sonic conditions. So, if you look at this friction will be dependent on what? It will be dependent on the Reynolds number, it will be dependent on the Mach number, it will be also dependent on whether the flow is laminar or turbulent, and surface roughness. That means, the pipe there will be different surface roughness, right. One can be smooth, it can be like rough, particularly those people who are in IIT K and who have already experienced winter season, like we will be getting a very warm water than the, because our tubes which are quite lengthy, number 1, and it is corroded, and we are pumping at a very high velocity, because pumping power we are giving, it is coming, water is drained, being dragged from a very low, very what you call lower height below the what you call level, that means very low level water we are getting, right, or in other words you can say that. So, then we will get this friction very hot, right, it is coming due to the friction according to me. So, now question arises how to get this actual value of f, because unless I know these f values I cannot really estimate, because if you look at this f I must know, right, unless I get I can't, but then it is depending on several parameters, Reynolds number, Mach number, that means of course and then surface roughness, laminar, turbulence and other things, right. For that we need to use this chart, that is friction factor diagram or Moody diagram, which you might have studied. If you look at this friction factor diagram, all of you will be familiar with, I guess, that friction factor is being plotted over in this axis, that is vertical axis, Reynolds number is being plotted in the horizontal axis, and if you look at these numbers are basically relative roughness factor, right. That means, this is a k divided by d, of course, this is a non-dimensional number. What you could observe here, that in this region, like where Reynolds number is very, very small, right, you will see that the friction factor is decreasing, right, with the increase in Reynolds number. and there is of course a critical Reynolds number, the transition is occurring, and this Reynolds number if you look at where is a very smooth, that means this one is a smooth pipe. If you look at this is a smooth region, right, almost negligible, you can say there might be another place where it is a smooth. So, if you look at these are all converging, and as the roughness increases, and Reynolds number is higher in this region, the friction factor is not changing, right. There is no changing over here in this region, there is no change, friction factor remaining constant, right. That is the beauty of that. Of course, there is a different roughness with the increase in roughness, it is increasing, but it is independent of the Reynolds number in this regime, certain regimes are there. As the friction factor increases, this regime are increasing, you can have a region, something like this, where it will be remaining constant. In this region, it is independent of the Reynolds number. That means particular friction factor. That means if I look at one kind of pipe, right, friction factor won't be changing, it is no more dependent on the Reynolds number. So, getting these values I can estimate F, and getting the F value I can do that. So, let us now take an example, consider the flow of air through the pipe inside diameter 0.15 and length 30 meter, right. It is a quite a huge length, 30 meter is quite huge. Otherwise, an inlet flow condition M1.3, that is subsonic flow, P1 1 atmosphere pressure, T1 273 Kelvin, and we are assuming the friction factor to be constant, that value is 0.005. If it is not given in the problem, you need to go back and do that, like calculate the flow condition at the exit of the friction things, like for example, in the station 2 you need to find out M2, P2, T2 and PT2. What we will do, we will from the isentropic table, that means see what is given here is P1 is given, T1 is given, right. So, and also the Mach number M1 is given, the Mach number M2 is not given, we need to find out. From the isentropic flow table corresponding to station 1, of course, the corresponding to Mach number of 0.3, I can get PT1 divided by P1 1.064, and I know atmospheric pressure P1. So, I can find out what is the total pressure 1.064 atmosphere, because it is same, right. There is not much difference, you could see, because the flow is subsonic and very low subsonic. Let us now, we need to estimate the M2. How we will do that? Because we know the length, we know the friction factor, but we need to now consider the sonic reference condition, the way we had done for the heat addition. So, for example, this is the flow what we are considering M1.3, P1 100 kPa, T1 this thing, and it is being certain length is given, that means here the length where the friction will be considering. See, this length is basically from here to this region length, right. In this case, what is that? That is something 30 meters, right. And what I will do, I will have to take this condition 1 and go to a where the flow will be sonic, that means M, this is the sonic condition, sonic flow condition. And then from that sonic condition, right, I will be coming back to the 2 to find out what is M2, P2, T2. That means, here I will get that what is this L1 star, and similarly when I will come from here to this region, I will get basically L2 star, but I do not know. So, therefore, what I know is, I know this L, this is given, I can find out what is L1 star, then I know that L2 star, then I will find out what it would be. Okay. and this is by using the table, we will be using a table, right. So, let us look at the Fano table, or we call it a table of Fano flow, and if you look at these are the values what we can get. That means, for point 3 P by P star is given, right. So, if you look at point 3, I will be getting this P by P star, T by T star, rho by rho star, P T by P star, and 4 F L star by D. And if you look at, I have given this inlet Mach number 0.3, 0.4 and 0.5, and of course, the 2, this is a supersonic condition, but in this example we will be using these numbers. We will see that we will have to interpolate between 0.4 and 0.5, we will see that how to do that, how we will do that. So, from knowing this thing M1 from the table of Fano flow, I can get 4 F star L1 star by D 5.299, and P1 by P star, I will get these values directly from the table. And then also the Pt by P star, and since L is 30 mm, I can get basically L1 star. I already got this because I know D, I know F, I can find out here. So, L2 star I will find out, right. And then I will estimate these values, what is that 4 F L star kind of things, and I will get these values. And if you go to this table, you will find these values is lying between these, like 0.5 and 0.4, because my values is lying between this L2 star, right. So, then I will have to interpolate, find out what is the Mach number it corresponding. So, that if we will do that, then I will get this Mach number is 0.475. This is the, and keep in mind that this is M2. Now, we got what will be the M2 here, and which is higher than the inlet Mach number, that is 0.3, right. So, then and also we will get all these properties T2 T star, P2 P star, and Pt divided by P T star, all those values. Then after that is very easy, P2 is equal to P2 by P star into P star by P1, and P1 this is known, and this ratio we know already, and P2 by P star we know, and we will just substitute, we will get this value. Keep in mind that P2 is less than what? Less than P1, right. And similarly, T2 by T star and T star by T1, you will just substitute the values, you will get that this is less than T1, right. And Pt2 is Pt2, you will substitute these values, you will get 0.728, and of course, it is less than Pt1, right. That means, there will be some losses, total pressure losses. Now, we have learned how to really solve this problem by what you call referring to the sonic conditions and then work on it. So, let us look at what happens to the Fano curve and how it looks, whether it is similar to the Rayleigh flow curve which you have seen. Again using the Moeller diagram, you can see that these curves shown here. If I consider this a subsonic flow at the station 1, what is happening with increase in the friction, that means, if I increase the length of the my tube, and then Mach number basically increases, we have seen in the last example. If I go on increasing my length for the same friction kind of pipe F values, right, then you will reach a condition where it is a sonic condition, right. That means, where the entropy will be the maximum value, this is S maximum, right. And similarly, when it is supersonic flow, then the what will happen, the Mach number will be decreasing and it will be coming to the sonic conditions, and this we call it as a choked flow, right. One is frictional choke, one is thermal choke, and also aerodynamically choke. That means, you cannot really go beyond that, and if you will do that right. If you want to change, the flow is choked, you cannot increase the mass flow rate. What is the meaning of that? You cannot really increase or you can't really change that one. So, naturally that means in this case, is it the mass flow is being choked or it is the friction? I cannot have frictionally change anything. If I want to change, I will have to change these inlet conditions, and particularly if you go on doing that in case of supersonic flow, then flow condition will change, and then you can have some shock formations like the way it is being done in case of a what you call Rayleigh flow, and then you will get a subsonic condition. So, let us summarize that what we have learned, that for the subsonic flow Mach number when Mach number increases with the addition of friction, m2 is greater than m1, and pressure is decreases, total pressure is decreases, of course, temperature is decreases, and for supersonic flow Mach number decreases, that means m2 is less than m1, and pressure of course increases, P2 is greater than P1, and temperature is increases, and total pressure is basically decreases in the both the case. So, with this I will stop over. If we are having any questions, we can discuss it.